we're going to design the bolts and the connections. So on the plates or on the connection, and our job is how many bolts and what size. That's the design process. The design process takes two forms. Okay, one, remember from last time, we have the slip-resistant connections, and we have bearing-type connections. The difference in the two, if the shear load is less than the frictional resistance, the connection is slip-resistant. Okay? If the shear load at the connection is greater than the frictional resistance, and that's the frictional resistance between the plates, the members will slip on each other and the bolts will be in shear, and this is called a bearing type connection. So what that means is, as we talked about last time, we're going to squeeze these plates together. It's kind of a difficult concept because the bolts are in shear and in tension at the same time. So when you put the when you put the lug nuts on your wheel, those lug nuts, if you don't tighten them down, then the lugs that are sticking out of the wheel are going to be in shear. And as soon as the pressure from the wheel is great enough, it'll shear off those lugs. Well, we don't want that to happen. So we use a pneumatic wrench and we tighten the wrench as tight as we can, or we actually go, as we said before, we tighten it all the way and then go a third of a turn further, and we create a slip-resistant connection, which means that the nut we put on the bolt is tightened enough so that we're squeezing in this case, the wheel to the axle of the car, and we're tightening it so much that the bolt is just squeezing those two materials together. So that's the difference between the same way when you're doing wood construction. The difference between screwing two pieces of wood together and nailing them together. When you nail them together, they're not slip resistant because you can't squeeze them together tight enough with the nails that you can't take the two pieces of wood and twist them against each other. But when you put in screws, you tighten the screws and it squeezes the two pieces of wood together so much that you don't get any slippage between the two. That's slip critical and bearing type connections. So last time we did a bearing type connection. So let's do one more. Here are the bolts. This example is for the bolts in shear and in bearing. The one difference about these connection designs are that we've already done the failure on the gross section of the plates. We've already calculated the failure on the net section at the location of the holes. And now we're going to do this calculation to see if what the capacity of the bolts is. If the capacity of bolts is greater than either one of those two equations that we did in chapter 4, then we're good to go. If the shear strength, in this case, if the shear strength of the bolts is less than either the net tensile fracture or the gross failure, then one of those two would control. So whichever one is the smallest will control. This problem says determine whether the connection shown. That's a pretty simple connection. Okay, here are the two plates. They're both 5/8 inch plates. We got 1, 2, 3. We got 4 bolts. One row of bolts in this row. Another row of bolts here. They're 1.5 inches from the edge of the plate, and 3 inches apart, and 3 inches apart. These bolts in single shear or double shear? Well, the bolts are in single shear. There's one shear plane right there. Okay. Now in this problem, the question is not how much load will this connection take. The question is, I put 60 kips of force on that plate, and say that plate is attaching a beam to a column. Okay. So I have this horizontal force of 60 kips R, and I'm going to use A 36-inch plates, 3/4 inch diameter, A 325N bolts. N means that the threads are included in the shear plane. Okay, so that means we get to use the maximum value for the capacity of the bolt, because it's being measured at the top of the threads, not down at the bottom of the threads next to the shaft. So what do? Well, in bearing, we need to do this same equation that we looked at last time. All right, the capacity for the first bolt, this bolt right here, what's the capacity of that bolt? Well, I need to know what the distance to the edge is from the edge of the bolt hole to the edge of the plate. That's 1.5 inches minus half of that hole. I need to know what the distance is from the edge of the hole to the edge of the plate, and that's 1.06 inches. Then I need to know the distance between the bolts. Where's the next line of bolts? Well, that's the center to center distance, or that's the distance from the edge of this bolt to the edge of that one, or 3 inches minus half this bolt hole and half that bolt hole. And there it is. 3/4 plus 1/8 is really one whole hole, so that's 2.13 inches. So that's the value of L that goes into this equation right there. Okay? So now we're ready to calculate the capacity for bolt 1. The capacity of the bolt is the phi factor, 0.75. L sub C is up 1.2 is the constant. L sub C is the smaller of these values. We just calculated 1.06. The plates are 5/8 of an inch in diameter. We have A36 steel, and notice in this equation we're using F sub U, the ultimate strength. So we use 58 KSI. This value, this inequality, value on the left has to be less than the value on the right. Phi times 2.4 times D, which is the diameter of the bolt, times the thickness of the plates, times F sub U. That's 48.9. The left-hand side of the equality is 34.6. So the 34.6 controls. Now for the bolts in the second row, okay, these bolts up here, all of the bolts don't have the same capacity because these bolts are further away from the edge, from the edge of the plate. So I'll check out those bolts, 0.75 times 1.2 times 2.13. Aha! The 2.13, remember, is the distance from this bolt to that bolt, the edge. All right? So there's the 2.13, 5/8 from the plate, F sub U. That value has to be less than 0.75 times 2.4 times bolt diameter times thickness of the plate times 58 KSI. So this part right here better than this part we figured before, and it is 48.9. And we have to take the smaller value of this inequality. Therefore, we'll take the 48.9 kips. So the total strength of the connection, considering that all the bolts are in bearing, okay, so all of the bolts have been tightened, is we've got 2 bolts in this first row, 2 bolts, 1, 2, they're each good for 34.6 kips, and then these 2 bolts in the second row are good for 48.9. So we'll add them together and we get 167 kips, which means for bearing on a 60 kip load, the bearing of the connection is adequate. We need to check the actual shear on the bolts. The shear on the bolts is phi times F sub n times A sub B. 0.75, 48 KSI is F sub n. That's the allowable shear on the bolt. Where do we get that? Get it from this table right here. And there's the tensile strength, there's the nominal shear. We've got A325 bolts. When the threads are not excluded, it says 54 KSI. I think this old problem's got a lower value. Yeah, it's got 48. This number right here. This number right here should be 54, not 48. 0.442 is the area of a 3/4 inch bolt. So in shear, each of the bolts is good for 15.9 kips. It's actually a little bit more because this value is from the previous table. And for those of you that got that are using the 14th edition of the manual, there's one of the differences is in the shear capacity of the bolts increased from the 14th edition to the 15th edition from 48 to 54. Anyway, we got 4 bolts. They're good for about 16 kips per bolt. That's greater than 60, so we're good to go. That connection will carry 60 kips. We would use 4 3/4 inch bolts in standard holes. Okay. Now, if we have oversized holes, then we have to use a reduction in the capacity. I think that's listed up here. Nope, I thought it was, but it's not in that table. Need to find where the capacity of the bolt would change based on the spacing in between the bolts. All right, now let's do a slip critical connection. Now we're going to squeeze the 2 plates tight enough together that they won't slip. So the nominal design slip resistance of a high strength bolt is this horrible looking equation right here. Like I mentioned to you last time, I think, and the time before, Now, for the slip resistance, we're going to have to take into account the smoothness or the lack thereof, the smoothness of the plates being bolted together. Okay, if you're bolting together, as it turns out, unpainted blast cleaned surfaces. I never did explain to you what blast cleaned is, because we haven't gone to a steel fabricator. But the steel looks the steel initially, when the fabricator fabricates the steel, it looks kind of rusty, and it'll have flakes, and where he drilled holes for the bolts, there'll be little burrs around the holes. The welds may not be real clean. There may be some crust yet on the welds. The last thing that the fabricator does before he puts the member on the truck for delivery is he blast cleans the member. And the blast cleaning is kind of neat. The member goes through a conveyor system, and on that conveyor system there's a box at the end, and that box has got it's got a bunch of BBs in it, or pellets. Okay, and the pellets get shot at the member. In fact, the member gets blasted with these pellets, and the blasting with the pellets cleans the steel, cleans all of the burrs off, and cleans the welds, and cleans any of the scaling and oxidation that's on the beam. So it comes out really nice and pretty. The surfaces are not smooth, they're clean. So you can see here that in this equation, there is a direct relationship. This mu right here is directly proportional to the slip resistance of the bolt, and there are the values of mu for the different surfaces, class A, B, and C. So again, I think one of the things, wait, I'm going up here, okay. See here where we've got Group A, Group B, and Group C, and somebody was asking me, hey, what's the difference between Group A, Group B, and Group C? Well, there you go. Now here, Class A surfaces, the mu is 0.35. They're unpainted, clean mill scale. That means that the fabricator may have brushed this steel member down with a wire brush or something before he loaded it on the truck. It's not blast clean. The Class B surface is. The Class C surface is if you galvanize the steel. If you hot dip the steel in zinc and galvanize it, then the surfaces are rough, but they're not as, the friction value is still not as great as it is for the blast clean surfaces. A few years ago, when we went down to visit the steel mill in Midlothian, across the street from the steel mill, there's a shop over there that they galvanize the steel, and they have this big, long trough, this big tub. It's a concrete tub that's full of hot zinc, and the steel members are moved over to this box and then dipped down in the box, dipped down in the box where the liquid zinc is, and they're totally immersed in this zinc, and then lifted up, moved outside, and dried. And they can galvanize anything. The day that we were there, they were galvanizing the some of the light towers that you see at highway intersections. You know, those big tall towers that have the lights at the top. This tub or trough that they were galvanizing in was long enough that they were able to dip that entire tower in the bath of zinc and lift it out, and it was covered both inside and out with the galvanizing. So a very interesting process. They also galvanize like chain link fence. They take a chain link fence and just dip it in this hot zinc. And they had workers in there that were in fire suits. The zinc would have a tendency where it cools on top, it gets a little crust on top of it, which makes it nasty to try to galvanize. And these guys had almost like squeegees. They look rakes. There were squeegees where they squeegee that crust off the top of the hot zinc so they could dip the next light tower in the zinc. Anyway, that's the story of blast clean and hot dip galvanized. What else is in this equation? D sub U. This is kind of stupid. D sub U is 1.13. It's a multiplier that reflects the ratio of the mean installed bolt pretension to the specified minimum bolt pretension. So there the bolt gets stressed to 13% more than its capacity. If that value is always 1.13, apparently it's too difficult for them to put 1.13 in the equation. So they put in a D sub U. The next term of the equation, H sub SC, is the hole factor. So remember the problem we just said, it was in standard holes. So if we were doing that same problem and trying to design it as a slip resistant connection, then for a standard hole, this H sub C would be 1. If the holes are oversized, then H sub C goes down to 0.85, and H sub C goes down to 0.70 for long slotted holes. So the value of the slip resistance of a high strength bolt can be reduced by as much as 30% for long slotted holes. Now, why would you use a long slotted hole in a connection? Well, if you wanted the two pieces of steel to move in and out, like at an expansion joint, for instance, you would use a slotted hole. Let me show you. I'll draw you a little sketch right quick. What actually happens at the fabricator is the fabricator, when he fabricates the beam, especially longer beams, the beams will have a camber on them. So here's a beam that has a little bit of a camber. And there's the end of the beam. Now I want to connect that beam to a column. Here's the column over here. Column straight up and down. And I'm drawing these two members separated. The column has a tab on it. And for illustration purposes, let's say that steel tab, it's welded to the column, and it's got heads where we're making a simple framed connection. So we're going to bolt those two pieces of steel together. One issue that we have with that connection right there, I'll draw it larger, is that the plate looks like that, and the beam is at an angle because it's cambered. So what they do when they fabricate the beam is they put in slotted holes. So now when I put a bolt in these holes, now I can straighten out the beam, and when I straighten out the beam, it'll rotate a little bit, but with the slotted holes, the bolts will remain in the slotted holes. So most erectors or most steel fabricators, their erectors will ask them to make the holes in the beams, in a beam to column connection, to make them slotted, so that when they go to erect the beam and move the beam up to the plates of the column, even though the beam, initially the beam has no dead load on it, so it's cambered, so they want to be able to put the bolts in it and then dead load it. When they put the dead load on, the beam settles down to straight, that these slotted holes then won't tear the beam. The beam will actually rotate a little bit in the holes. And I draw it exaggerated, obviously. In real life, it's a very small amount. Okay, so that's the H sub C. The T sub B is the minimum fastener tension from table J 3.1. Table J 3.1. We've seen that before, haven't we?
The blinds, and I was like, oh.
Up there's 3.2. So I said we haven't seen J 3.1 yet. So if you look in the steel manual, you can find table J 3.1, and J 3.1 would give you the fastener tension. Okay, so take my word for it before I open up the steel manual and go to table J 3.1. Then N sub S is the number of slip planes. That's the last value in the equation. The problem we just did, there's one slip plane, right? One shear plane where the connection will slip. So let's do an example problem. Now we're going to do a slip-resistant connection for the lap joint. It's shown here in figure 12.9. The axial service load, service load is 27.5 kips. The live load is 40 kips. Determine the number of 1-inch diameter A325 slip critical bolts in standard size holes are needed for the limit state of slip if the faying surface, that's the roughness of the surface, is class A, that's what we just talked about. The edge distance is 1 3/4 inches. The center to center spacing of the bolts is 3 inches. The F sub Y of the plates is 50 KSI, and the F sub U of the plates is 65 KSI. There's the picture. So how much load are we going to resist? We're going to resist 1.2 times the dead load plus 1.6 times the live load, which is 97 kips. So we got 97 kips pulling on these two 5/8 inch plates. And if we find the nominal strength of one bolt, then say the nominal strength of one bolt is 50 kips, then it would take 2 bolts to resist that load. So we're going to plug and play in that equation and see if we can come up with the capacity per bolt. There's the equation. Class A surface means that mu is 0.3, D is stupid, it's always 1.13. T sub B is the bolt pretension from table J3.1. The hole factor, we have a hole factor of 1 because it said we're in standard holes, standard size holes. So the hole factor is 1. The number of slip planes is 1. So we're good to plug and play. So we got 0.30 is mu, 1.13 is D, 1 is the hole factor, 51 kips is the tension, bolt pretension, 1.0 is the number of slip planes. We got 17.29 kips per bolt. So the slip critical design to prevent that slip is 17.29 kips per bolt. If we got 97 kips, wait for it, 97 divided by 7.29 is 5.61. Don't put in 5.61 bolts. Let's put in 6, all right? So we got 6 bolts. Now that's the number of A325 bolts with the slip critical connection. Let's just check to make sure that the bearing strength of the 6 bolts is all right and the shearing strength of the bolts is okay. So here's the bearing strength of the bolts. There's that L sub C from this equation. The lesser of 1 3/4 was the edge distance minus half of the hole, or we said they were 3 inches apart. The spacing the bolts 3 inches apart. So that's 3 times 1 bolt hole, 1.8, 1.187. So we'll plug and play in the bearing. 1.2 times 1.8187 times 5/8 for the thickness of the plate. F sub U of the plate is 65 KSI. The number of bolts is 6. And the bearing is 347.2. That's way above the 97. Remember that inequality. This value has to be less than the right-hand side of the inequality, and in fact it is. Then that means that the minimum value is 0.75 times that times R sub n. 0.75 is the phi factor of this equation. Phi right there is 0.75. And that gives us 240.2, which is greater than 97. So all is right with the world. The total, notice that I've got here, I've calculated the total shearing strength of the bolts is the F sub NV, the value of the allowable stress of the bolt, the number of shear planes in the area of the bolt. That's 68 KSI. There's 1 shear plane. The bolts are 7/8 inch diameter bolts, 6 of them. Right. Bolt holes. The sizes of the bolts are 7/8. We use 7/8 of an inch. So multiply that times the 0.75 and you get 240.2. So the bolts are not going to shear. The bolts are not going to fail in bearing. The connection is going to fail the connection will carry 6 bolts, 6 1-inch diameter bolts for 97 kips. Technically now you need to figure out what's the net tensile capacity of the connection and what's the gross capacity of the connection. But this question just asked for the number of bolts. Okay. So let's do one more. Here's a slip critical connection. Here's what we just did again. The A325SC are the slip critical bolts. We have a Class A surface. The slip is the serviceability limit state. So we'll do the same thing we did before. Here's the capacity of bolt number one, and based on an L sub C of 1.06. That gives us 28.8 kips for bolt number two. We do the same thing. We get 40.7 kips. The strength of the bolts is 2 bolts at 28.8 kips. 2 bolts at 40.7 kips gives us 139. And notice it says that's greater than 60, but if we're checking in this problem, then we'd be greater than the 97. Okay. So that's bolts 101. The homeworker problems, there are 2 of them that I posted to the Canvas. The 2 homework problems. Okay, the first is homework number 9, and homework number 9 says there are the 2 5/8" plates, A36 steel, LRFD design, the 10-inch wide plate. And when you're doing these problems, the narrower, smaller plate will always control. So that's what we'll check. This is the analysis problem. How much live load will the plate support? Okay, based on 6 1-inch diameter, A490. The SC means these are slip critical bolts. So you do exactly what we just did in the previous problem. There are all of the dimensions of the bolt, so you can get the values of L and calculate the slip critical value. You'll get one value for this row of bolts, one for this one, and one for this one. Add the values for the 6 bolts together, and you're good to go. In homework number 10, and this didn't print very good. Those are bolts right there. Okay, in homework number 10, it says we've got a truss member. So this is a gusset plate, and if we were to take this and turn it like this, right? It's one of the braces for our building where it comes to the gusset in the middle. The braces themselves are 2 pieces of channel, C12 by 25. And the problem says that they are connected to this 1-inch gusset. They're the dimensions. And I didn't say what size, I didn't say how many bolts. The question is how many 7/8" diameter A325 bolts. The threads excluded from the shear plane are required to develop the full design tensile capacity of the members if they're used in a bearing type connection. There's the value of U. So you got 2 of these C12 by 25s. You need to find out what's the maximum capacity of the 12 by 25. So you got 2 of them, okay? And 2 of them, I think that now is the time to look in the steel manual. Just a sec, let me get it up here. All right. Okay, here's the steel construction manual, and we're going to look for the C12 by 25. What's the area of a C12 by 25? The reason that I'm doing this is that I think never mind, I was wrong. I was thinking that they had values in here for the C shapes when they're back to back with the gusset plate in between, but they don't. So here is the C12 by 25. The area is 7.34 square inches. Okay, so you have two of those. That's their gross area. So first of all, what is the capacity based on the gross area? Well, it's F sub y times A sub g. All right. Then based on the net area, the way the holes are configured, it would be the gross area minus 2 holes, and the U factor is 0.85. So you can find the net area capacity, and that gives you, for the problem, that gives you the maximum of the two C. What you need to do is, once you know what piece of U is,
Hey.
Is this okay?
Oh yeah. We're working around each other. Thank you.
How's it going? What?
so once you know what piece of U is, now you can, I showed 6 bolts in here, but put the bolts in 2 rows like that, and do exactly the same thing that we just did in that prior example. What's the capacity of the 6 bolts? So if you start off with the 6 bolts, or you find the capacity of the bolts in each row, the combination of bolts needs to exceed the value of the 2 channels back to back in tension. So work on that problem between now and Wednesday, and I'm going to work it out, and if you play your cards right, I may show you the solution to that homework problem, and we'll do that on Wednesday. And then, as I said before, chapters 12 and 14. Chapter 14 is the welded chapter. We're going to go through welding probably in just 1 or 2 lectures, and we're going to have an exam on bolts and welds, and we'll move on then to the analysis and design of beams. Okay. So there are your homework problems. I'll go to work getting your exams graded, and back to you as quickly as I can. I have a couple of doctor's appointments this week.
No, we're actually about to sit in a meeting, and I was going to ask if we'll be too loud if we have it in the hallway.
A little bit behind, but
On the
don't worry, I'll get it done. That's
Down
it
here?
for today. We'll see you
Okay.
all. We'll see you all
the bathroom, the hallway with
same
restrooms
time.
is the next door to your right. I know what my right is.
Okay.
Okay, thank you.
You betcha.
Okay, thank you.